Hello, everyone. Welcome to the session on building event-driven applications with Amazon DocumentDB with MongoDB compatibility. My name is Varma Gotamakala. I'm a database specialist solutions architect here at AWS. And then I'm here with me. I have Saurav Biswas. Saurav, do you want to kind of introduce yourself?
Yeah, hi everyone. I'm Saurav Biswas. I'm a specialist solution architect with the Amazon DocumentDB team. Thanks,
Th-
Varma.
Thank you, Saurav. So let's get going. Today, right, this is a brief agenda of what we're discussing today. We're going to talk about Amazon DocumentDB, its architecture a little bit, because Amazon DocumentDB, we have two different versions. One is instance-based clusters, and the other one is elastic clusters. We'll be talking briefly about both of them. And then we'll also talk about an important piece, which is basically our Lambda event source mapping that helps you kind of stream the data from DocumentDB to any other AWS services. So today we'll be showing two demos as well. One with ESM integration with OpenSearch, and then Saura will also kind of show you how we can push the data from DocumentDB to Redshift using ESM. And then we'll discuss next steps, and then we'll show some resources which you can utilize. So let's get going. So first, right, what is DocumentDB? Amazon Web Services offer over 15 purpose-built database engines to support diverse data models. Amazon DocumentDB, right, that's the topic in discussion today, is a purpose-built document database that is scalable, highly durable, and fully managed database service for operating mission-critical JSON workloads or MongoDB compatible workloads. DocumentDB service has two different types of clusters: instance-based clusters and elastic clusters. So let's get started with the instance-based DocumentDB clusters. Traditional database architectures, right, were not designed for the cloud. They are built as single monolithic architectures. They scale monolithically and they fail monolithically, optimized for single instance with a disk attached to the compute itself. Everything built on single physical machine. Uh, for example, API you need to talk to your query processor, which is responsible for figuring out how to get the info you're asking for, your working set cache for performance, your write ahead logging, and all those things, right? Or and even storage, they're all part of the single infrastructure. If you need more of something, say a local cache, then everything needs to scale together and will fail together. This architecture, right, brings in a number of challenges. For example, if you need more read capacity, the only way to achieve this is add another node to the cluster. Copy all data from primary to the new node first, and then if you could, it could take a long time depending on the amount of data you have, right? And then second, this draws resources from your primary as it needs some compute power to copy the data. The same goes with node failures. If your node fails, you need to spin up a new node and copy the data to the new node. And then if your storage needs to grow, you need to swap to a bigger disk, and there's a limit to the size of the disk based on the instance size. At some point, you might have to scale up to a bigger instance size, and it also has a limit. And another challenge you see is backups. Whenever you back up to your primary, right, it draws resources and impact the performance. A lot of customers to get around this, right? What they do is they spin up a dedicated backup node just to use for backups, and this is an awful waste of resources just for the purpose of backing up your data. And then another challenge is your data is still sitting on the disk attached to the compute, and the data is not really highly durable because a disk failure can, you can lose your data. And then here is a typical monolithic architecture for a typical database which is not architected for the cloud. And then when we set out to architect a cloud native database service, we decided to decouple the compute and storage layers. Because of this, you can scale compute and storage independently of each other. The key design consideration that we have with DocumentDB is really about splitting the compute and the storage so that the compute layers are responsible for accepting connections and responding to the client requests, processing the queries, and giving results back to the clients, and also handling the caching of results for performance improvements. And the storage layer is separate. The storage layer leverages a distributed storage volume that we have built over time, and that allows for the compute layer to scale independently of the storage layer. We'll talk about how that affects some of the scenarios that we were just talking about. So here is a simplified version of the way to look at it, right? To look at DocumentDB. At the bottom, we have this distributed storage volume that has been built for the cloud. It is distributed across three availability zones in the region. When you store a block of data into the distributed storage volume, it is stored twice in each of the three availability zones. That means we store six copies of your data. You see the green boxes here that is stored six times. So that's always making it a durable and available storage choice that's going on in the back. And then no one is really ever interacting directly with the storage volume. You interact with these instances at the top that you can have between 1 and 16 instances. One of those instances will be the primary, and all of the writes will go through the primary. The other instance from 0 to 15 of them, right, they are actually read replicas. They are replicas that serve two purposes. One of them is that they can serve reads, and then so that you can route reads to any of those instances, and it will be able to answer that request. And then they also serve as a standby. If there is a failure of the primary node, DocumentDB promotes one of the replicas into being the primary and then shorten the amount of time it takes to respond to that. Typically, it's done around under 30 seconds. And then there are like a number of choices for the instance types, similar to the other AWS services, where you can go from relatively small instance sizes, like 2 cores and 4 GB of RAM, all the way up to very beefy machines with 96 cores and 768 GB of RAM, and a bunch of options in between. And so you can deploy as many of those as you need to. Now, let us see how Amazon DocumentDB handles failures and how backups are done. Let me start with compute. If a primary writer node fails, an existing replica is promoted to the primary. And you can always set a priority on what replica you want to set as a backup or like a standby. And then this is typically within 30 seconds. And then a new instance is launched to replace the failed instance, which will come up in about 8 to 10 minutes, bringing the cluster back to its full capacity. If a replica instance fails, it is replaced with a new instance. Again, there is no need of failover, as there is a no need to as there's no data to be copied, because the data, as you remember, as I mentioned, right, the data is always stored in a distributed storage volume, so you don't need to copy any data. And then this the replacement node will take anywhere from 8 to 10 minutes to come up, but your failovers happen within 30 seconds if you have a more than one node. And coming to the storage, right, Amazon DocumentDB uses a unique, distributed, fault-tolerant, self-healing storage system. When a segment of a cluster volume fails, Amazon DocumentDB immediately repairs the segment, usually using the data from the other volumes that makes up the cluster. Backup in DocumentDB is different than how traditional backups are performed. DocumentDB backup has no impact on performance because we stream the backup from the storage layer to S3. We perform continuous incremental backups at every 5 minutes and full backups to S3, so that we have fine granularity with incremental backups and a faster restore time with the full backups. And the DocumentDB is highly durable by default. It can handle an availability zone failure plus for writes, and an availability zone failure plus one storage node failure for reads. Because we use quorum for reads and writes, we require a quorum of 4 for writes and a 3 for reads. That means that we need acknowledgement from 4 of the storage cells for a write to be successful, and then 3 from of the storage cells for the read to be successful. Amazon DocumentDB is designed to store, index, and query rich and complex JSON documents with highly available scalability. You can retrieve documents based on nested field values, join data across collections, and perform aggregation queries. So, if you need schema, flexibility, and the ability to index and query rich, structured, and semi structured documents, Amazon DocumentDB is a great choice. Amazon DocumentDB clusters provide 99.99% availability, that's 4 nines of availability, with highly durable storage, which maintains 6 copies of your data in 3 availability zones within an AWS region. Amazon DocumentDB instance-based clusters can handle tens of thousands of write operations per second and millions of read operations per second, with one primary and up to 15 read replica instances. And it can support up to 128 TB bytes of data. While Amazon DocumentDB Elastic clusters with 32 shards can handle workloads requiring petabytes of storage and millions of read and write requests per operations per second. I'll talk about Elastic clusters in a bit. Amazon DocumentDB architecture lets you scale your database in or out, up or down in minutes. irrespective of the data size. Because as I said, right, our storage is distributed storage volume, which is completely separate from the compute. AWS manages the underlying hardware, operating system, and database software and takes care of maintenance, patching, and failovers, freeing you from doing the undifferentiated heavy lifting of managing the database infrastructure. The third pillar is MongoDB compatibility. This is important to many of our customers as they bring a lot of workloads that are developed using MongoDB. DocumentDB supports MongoDB workloads and is compatible with the MongoDB API. It is a logical choice for MongoDB users who are looking to easily migrate to a fully managed database solution. You can use the same tools, drivers that you used with MongoDB to work with DocumentDB. You can lift and shift applications to DocumentDB with little or no code change. Please note that Amazon DocumentDB is not a MongoDB under the covers. It's built from the ground up as a cloud native database in AWS. We support hundreds of APIs, operators, and aggregation stages from MongoDB API. And if you are using any MongoDB operator or API that is not yet supported, please let us know as we are always working back from what our customer wants. And Amazon DocumentDB cluster provides 4 nines of availability, can handle tens of thousands of writes per second and millions of reads per second, and supports up to 128 TB bytes of data. And then coming back to the Elastic clusters, at reInvent of 2022, we launched Amazon DocumentDB Elastic Clusters, which is a new type of cluster aimed at providing even more scale than instance-based DocumentDB clusters. With Elastic clusters, we aim to support millions of reads and writes, as well as support petabytes of storage capacity. Let's take a look at how we actually achieve scale with Elastic clusters by looking at this architecture. While what you're seeing here is the documented instance-based cluster architecture, where it can support up to 128 TB bytes of data and tens of thousands of writes per second. With Elastic clusters, what we have done is we have used this as a building block so that what we have done is imagine this each one of these clusters now becomes a component of the Elastic clusters and is known as a shard. What we've done is we have stitched these clusters together or these shards together, and now these are the components of Elastic clusters. And together, this is how we are achieving that millions of writes per second as well as petabytes of storage capacity. Let's take a look at like some of the characteristics of Elastic clusters. We have a very similar set of characteristics as discussed with our instance-based clusters, and under fast and scalable, the key call out here is that Elastic clusters support millions of writes as mentioned and can scale up to store petabytes of data. In terms of scaling speed, in some configurations and with Elastic clusters, you do not need to worry about provisioning IOs in advance. The IOs are handled, IO provisioning is handled automatically under the cover. The last point I'd like to call out here is that most queries can complete in milliseconds, and this again depends upon your query. Of course, if you're doing a lot of aggregation or computations, it may take a little longer. But again, most queries complete within in milliseconds. The second point here is it's fully managed. So similar to instance-based clusters, where we aim to provide administration so that you can focus on your app, we are doing the same thing here. So you could expect built-in high availability, durability, and security as well. And the last point is MongoDB API compatibility. So very similar points to them before. The goal here is that you can use existing MongoDB application drivers and tools. And very similar to what you have been using with DocumentDB if you're using it already. We aim to support hundreds of APIs, operators, and stages. And then as we move forward into the future, one thing that we're going to be able to do is as we launch new features, we're going to be able to see these capabilities and features in both Elastic clusters as well as instance-based clusters. If you're already using that, so no need to switch. Applications can run well on instance-based clusters as well. And with that, I'll pass it on to my colleague Saurav Biswas, who's going to talk about AWS Lambda event source mapping. Over to you, Saurav.
Thanks, Verma. Now let's talk about AWS Lambda event source mapping and how it enables us to build event driven applications with Amazon DocumentDB. So let's talk about an event driven design pattern. What is it? What makes it special? It is a decoupled architecture where a source creates and publishes events which are transmitted via an event broker to a subscriber or consumers of those events. So this is the flow of events that happen. In our demonstrations today, Amazon DocumentDB will be our event producer, publishing all data changes happening in the cluster to the change streams, which acts as our event broker. AWS Lambda functions would subscribe to those database events and send them downstream to different services. We'll talk about Amazon Redshift Cloud Data Warehouse and Amazon OpenSearch Service as those target systems today. So, to enable event driven architecture with Amazon DocumentDB, we need Amazon DocumentDB change streams. What are Amazon DocumentDB change streams? They provide a time ordered sequence of change events that occur within your cluster's collections. Keep in mind, they are not turned on by default. So, when you start a cluster, they're all turned off. You have to explicitly enable them. There's a default retention period of 3 hours, but you can extend it up to 7 days depending on your use case. So if your consumption needs an extended retention period, you can always retain it for more than 3 hours to up to 7 days. Keep in mind, it can only be opened from a connection to the primary instance. So if you have a lot of connections happening to your cluster, if that's your application requirement, you have to take into account change streams as well if you're consuming them. And then change streams incur additional read and write IOs as well as storage costs. So keep that in mind while enabling them. So that's why maybe it's prudent to not enable change streams on all collections, but only those that you need. Now let's talk about how change streams are created. You have an application that writes data to Amazon DocumentDB engine. In this example, the application is sending over an update command. DocumentDB will first make sure that the data is written or updated in the storage as well as the cache. And at the same time, once it has persisted the data, it will also persist that event which captures the data change in change streams, which actually are being stored in a storage layer. Now let's see what enables Lambda functions to be triggered by those change streams. So Lambda ESMs or event source mapping is a Lambda resource or utility that can read from an event source and invoke a Lambda function. Lambdas now support Amazon DocumentDB change streams as an event source, and it leverages the change streams that are stored in the DocumentDB storage layer. And now, with the help of change streams and the ESM, you could build event driven applications on Amazon DocumentDB. Now, before ESMs, you could still consume change streams using the API. But with ESM, you have a managed solution which automatically takes care of periodic polling, batch handling, error handling, state tracking. So it's a much simpler management as compared to how you would do it before event source mapping was introduced for DocumentDB. And this is again a typical workflow of how we are going to read from a change stream. A Lambda function would periodically send get event calls to your DocumentDB, and the DocumentDB will get those change streams and send them over to the Lambda function, which in turn can send it downstream to any service that it needs to. Now let's see them in action. Over to you, Verma, for your OpenSearch service integration.
Okay, so I will be talking about OpenSearch service integration with DocumentDB using ESM. So as mentioned, right, as Saurabh mentioned, the Lambda ESM launch simplifies data streaming from Amazon DocumentDB to other AWS services. Here, I will demonstrate you on how you can use Lambda functions to stream your DocumentDB data changes in real time, near real time, to the Amazon OpenSearch service index And then OpenSearch, right, can index and run fuzzy full text searches on the semantic search queries. Here is the architecture diagram of the implementation that I'll be showing today. I will simulate application rights to Amazon DocumentDB by importing a sample review data set using a Python programming language, and then on running on AWS Cloud9. AWS Cloud9 is our web-based IDE. We'll write the data using that Cloud9 to DocumentDB, and then Lambda ESM will actually capture those changes, and then it will run whenever there's a change coming in, and it will push the changes to Amazon OpenSearch service. And then we'll use the secrets managers to store all the credentials for the DocumentDB for this Lambda ESM. So before I kind of start loading the data, right, I want to kind of show you a few things. The first thing is uh, the Lambda ESM. So this is the Lambda that we built. Basically, this is what I'm showing here. The code is kind of pretty simple, right? Here we see it's a handler. That's kind of how you always build a Lambda. You have a handler that handles any stream or changes that are coming in. What it is doing, it is reading from the document DB here, and then it's actually posting that changes to OpenSearch. And then we are doing it in a like batch fashion. And then if I show you the configuration, this shows here, this is a trigger which for the document DB. This is the my document DB cluster. And then here I'm showing you it is using the basic auth, but it's showing this is for the database is product reviews DB, and then the collection is product reviews, and then it's doing at a batch size of 100 events at a time. And then I'm storing all this in a secrets manager. So this is my setup for a Lambda ESM. And then I have like a document DB cluster setup here, which is like a pretty simple cluster. It's just a one node for this particular demo. But you can, for a high availability, we always recommend to have one primary and at least two replicas. That will give you 4 nines of availability. And then with that, right, what I want to start is I want to kind of load some data into my document DB. So I have a script here, loader.py, and then I'll be loading that. So it will take a few minutes to kick off, a few seconds to kick off. Once it starts, then I will start interacting with the OpenSearch. So while it goes, let me switch to the Lambda ESM, and then I can monitor changes that are coming in here. It just takes a few seconds to kick off, and then here, as you see, reviews are added. Each review is added. Right now, about 3,000 reviews are added, and then this should pick up pretty quickly than what we are actually kind of processing. And then while it does it, what I want to do is I want to basically kind of log into the OpenSearch, at least the cluster, and then show you how we can interact with it using OpenSearch. So to do that, what I want to do is I want to kind of get my host name for OpenSearch. Okay. I will, because we use the CloudFormation template to run this, so I'll go to my CloudFormation to get the domain endpoint for my OpenSearch so that I can use it here. And here is my OpenSearch domain endpoint. So I'm copying that and then paste it here. And then I will just put that in my bash profile. And then I will just use a curl command to interact with OpenSearch to see if the changes are coming into OpenSearch. So as you can see here, right now I have about like 600 docs that are in the OpenSearch, and then the data is going into OpenSearch. So now, what I want to do is I want to show you a few queries, right, that you can run on OpenSearch to see if that I can do a full text search or a fuzzy text search using the OpenSearch with the DocumentDB data that is streamed from DocumentDB. So the first query I want to try out is I want to kind of search based on the review body. I want to kind of see all the documents that have, say, easy to use text as well as with a review rating of more than a 4. So this is a query I'm kind of running on this. So it basically, right, it's a query that has a review body, easy to use text, and which has a rating of over 4. So if the data is kind of streaming in, right, it should show me the results that has the text and the ratings of more than 4. So this is basically how you can do full text search, and that's one use case. And then other than this, right, I can do like a there's another feature in OpenSearch called where I can boost my query. That means that, for example, right, you I want to match I want to match for a game, and then in the review body, I want to kind of see I want to boost the score twice. So I'll show you the query, then it makes you can understand kind of what I'm talking about. So this is the query I have here. So as you can see here, I want to kind of boost the query game, and I want to do the review body. I want to boost it twice. So it means that this is a higher priority I want to give for my review body. So if I use that and then search on that, it should give me results matching that particular query. So as you can see here, I got this games in the search body. That's kind of the boosted, and that's another query I can do. And then there's another text search which is normally what we do is like fuzzy search. For example, right? For example, consider this word easy. That's spelled as EASY, but typically, like a lot of times when we're searching, we might kind of misspell it. So in here, I'm misspelling it as EASI, but it will still kind of look for words, documents that has the actual word that I'm looking for. In this case, easy. So I'm using this search here, which should give me results which has, say, easy in my string. So as you can see here, that gave me results that has that easy in here. And then this is another search, and then there's another search which we can do here is searching with synonyms. This is all kind of things which will be supported with OpenSearch, but the power here is that basically, right, you're using the data which are part of the document DB, and that is streamed into OpenSearch using that lambda ESM. So here I'm using the synonyms. For example, I'm searching for something called a software in the review body, but a software, another synonym for software is like a program. So it should return me results which has program in its body as well. So I search on that, and it should give me uh, the the documents that has the program or software in the review body. So that's kind of all the different use cases that you can use to interact with OpenSearch, especially with the data coming from DocumentDB. With that, I would hand it over to my colleague Saurav to do the demo on Redshift integration. Over to you, Saurav.
Yeah, thanks, Varma, for your demonstration of how to use OpenSearch with DocumentDB. In this following demonstration, I'm going to talk about how to integrate Redshift service. Redshift is a cloud data warehouse built on AWS. It can do massively parallel processing on petabyte scale data for all your analytical needs. Now, this architecture is going to be a bit different from the one that we saw for OpenSearch. So in this one, we have an additional component, which is the Kinesis data firehose, and we're going to talk about why we need this component while integrating with Redshift. So OpenSearch can accept JSON documents as is and process them, but Redshift is different. Redshift requires tabular row column format. So you can see the need for a transformation logic here. Also, the architecture would tightly couple two distinct responsibilities, right? So one is getting the data, the other one is transforming the data. Hence, we're introducing Amazon Kinesis Data Firehose in order to decouple and achieve separation of duties. This will also maintain performance on the individual components. The first Lambda function would read and transmit the changes downstream to a Firehose data stream. The Firehose data stream would stage the data, batch them as per configurations we provide, and invoke Lambda functions to transform them. Once the data is transformed, it will be sent to an Amazon Redshift table that we can configure again from the AWS console. Once your data is in Redshift data warehouse, you can run all your SQL analytics. In fact, you can connect any BI tool. If you're using Amazon Athena, you can connect that to Redshift and then run your analytical needs and workloads. So I hope it clarifies why we need that extra component here in this architecture as compared to OpenSearch. So this is my AWS console home. You can see all the recently visited services. So I've set this one up already before starting the demo, and I'm going to walk you through the different components. We have a DocumentDB cluster. In this case, if you see, I have created a highly available cluster. So this is the setup where in case if the primary were to fail, the failover will happen in less than 30 seconds. An ideal setup for your production workloads. As you can see, this cluster is placed in US West 2 region and it has three instances. Out of the three, one is a primary, the other two are replicas. And as you can notice, each of these instances is its own availability zone. So instead, in case there is an outage in one availability zone, it doesn't impact the availability of your cluster. Failover happens in less than 30 seconds. I've also set up a Cloud9 environment where I've created an mock setup for sending data over to my DocumentDB cluster. In this case, I'm using an open source tool called NoSQL Bench, which is a commonly used tool for mocking data and creating a demo workload on any DocumentDB cluster, or you can use it with other NoSQL databases as well. So what I'm going to do, this is the results from the last run, but I'm going to fire up a new test, which will load 1 million records into DocumentDB. As you can see, I'm using the database demo underscore DB for my test purposes. Now let's go and check the data in DocumentDB. So I'm going to connect it using Mongo Shell and then use demo underscore DB database. As you can see, it switched to demo underscore DB. And then the collection I'm using is customer underscore activities. And I'm going to show you what is the count of documents there, right? So close to like 4 million documents that you can see here. You'll see that it keeps increasing because my tests are running. Now let's take a look at what a document looks like. So I'm going to run the find one command, and this will give you what this document looks like. So there is a customer ID field which identifies a customer in our mock scenario, and the customer does different sale activities, which is an array of sales. So as you can see, it has an activity date, a quantity, a source, then a total price, and a product name, right? So it could be anywhere between 1 to 3 activities per document. That is my setup. And then, as I had mentioned before, we do not have chain streams turned on by default. So I had to turn on chain streams in order to make the setup work, which I've done already. So let me show you what are the chain streams that are currently enabled in our database. So I'm using this command. You can find it in our documentation, but what it shows is two outputs. The first line basically indicates that I've turned on change stream for all databases and all collections. Since this is a demo, it might be fine, but never do it in production. Always carefully choose the collections you want change streams turned on. And then, if you were to choose just the customer activities, it would look something like this, the second line. Well, because we have everything turned on for all collections, the second entry does not really have any effect, but you could do it when you're doing it actually in production. So we saw our data that is flowing into document database. Next, we need a Lambda function that will read these changes. And it's very similar to the one that OpenSearch had. So we have a piece of code that is reading those changes. And as you can see, all it's doing is sending these records downstream to a data firehose, which is identified by the stream name, right? This is all it's doing. So again, separation of duty, decoupling. My trigger looks similar to what Verma had showed. So not going into the details of it, but you can see it's looking at collection customer underscore activities and in the database demo underscore DB. Further downstream, we have our Kinesis data firehose. Again, I'm not creating them, but these two have been pre-created for the demo, right? All of these artifacts. So if you really look at my setup here, I have a few things that are critical. One is I'm transforming this data using a Lambda function. You can set up buffer size, buffer intervals. The documentation mentions how to do that. But if we take a look at the flattened JSON data Lambda function, you will see it does a lot of transformations here. Essentially, it's getting each individual activity that we had shown in the DocumentDB collection, and then inserting customer ID into that particular document and creating a new line in your records. So it's making it ready for Redshift consumption. Once the Lambda function returns the data after transformation, you see that it will be sent over to a Redshift destination. In our case, we have a serverless Redshift setup, and we are sending them over to the dev database under the table called customer underscore activities. So same name. Now Redshift data copy happens using the copy command. So we need an intermediate S3 destination for it. If you look at the S3 destination, you will see in the S3 destination bucket, you will see there are different folders created, manifest, and under the folders that are prefixed by the date and then the hour, you will see different files that are being copied over by the firehose. And then firehose also manages periodically running this copy command. Keep in mind, this copy command also has different parameters that we can inject. And in our case, I've injected a time format and date format because I need the flexibility to read my document DB data properly. So as you can see again, this is separation of duties and decoupling live in action. And finally, we have our Redshift serverless setup. We are using the Redshift demo namespace, and you can click on query data that opens up a query editor for you. You could also use Athena or any other BI editor. I'm using the query editor because it's just easier to use and it's pre-integrated with your Redshift deployment. So under that, we have the dev database, we have the public schema, and we have the customer table, customer underscore activities table. If you double click on it, I can see that it basically maps one-on-one to what my document structure was with the addition of customer ID, which maintains a relationship between the different documents. Now let's run a couple of queries just to give you an idea of what Redshift can do. You can always run a count of all the documents. So you see, we have a lot of documents here. I've been ingesting a lot of data and archiving it in DocumentDB. So Redshift has way more data than DocumentDB would have. So keep this in mind. DocumentDB is for OLTP, Redshift is for OLAP. OLAP always has usually more data because you're putting a lot of historical data there. So you see, we have a lot, close to 30 million documents here. And then if you further go down, this is a typical query. Now, this query is a simple one, but just to give you an idea of how Redshift can do massive parallel processing and give you results super fast, as you can see on the screen. So this is a daily breakdown of total sales by quantity and price. So this is the demo architecture for integrating Redshift with Amazon DocumentDB by utilizing chain streams and LambdaASM. So I hope these two demonstrations help you understand how to utilize LambdaASM to build event-driven applications with your Amazon DocumentDB database. Before we end today's tech talk, I want to leave you with some resources to get started with Amazon DocumentDB. Do utilize our free trial so you get 1 month or 750 hours of trial period where you can use T3 medium instances. You get 5 GB of storage and 5 GB of backup. You also get 30 million IOPS. So all of these resources are free. It's good to get you started without spinning up your own instances. You should also take a look at the resources out here that I am highlighting. So one is the blog that kind of talks more in details about the architecture Verma demonstrated. And then we have a resources page. In that page, you can get linked to a dev guide, all our blogs, articles, customer references, FAQs, everything you might need to get started with DocumentDB. Thank you so much for your time today, and do leave your feedback and hoping to hear back from you.
Thank you, everyone.